Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. In the last few sessions, we were focusing on combinational circuits like adder, subtractor, magnitude comparator and code converter. In this class, let me introduce you another commonly used combinational circuit, decoder. What is a decoder? A decoder is a digital circuit that detects the presence of a particular binary sequence at the input level and indicates the same at the output level. We know that in digital systems, discrete quantities of information are represented using binary codes. Also, you may recall from the previous sessions that an n-bit binary code can represent 2 raised to n distinct codes. For example, a 3-bit binary number can be used to represent 2 raised to 3, that is equal to 8 distinct codes such as 000 to 111. Similarly, a 4-bit binary can represent codes from 0000 to 1111, that is 16 distinct elements. In general, a decoder is a combinational circuit that transforms the n-bit binary information to 2 raised to n unique output lines. One of these 2 raised to n output lines will be high depends on the input binary sequence when the decoder is enabled. Or we say the function of a decoder is to detect a particular binary input sequence and indicate the result by one of the output line. The 2 raised to n outputs of a decoder are actually the 2 raised to n minterms of the n input variables. The decoders are usually presented as n to m line decoders, where n is the number of bits at the input level and m is the number of output lines. M can be less than or equal to 2 raised to n. The decoder is symbolized with a rectangle where n input lines are drawn at the left of the symbol and 2 raised to n output lines are drawn at the right. It is the logic diagram of a n to 2 raised to n decoder. Before we move on to the different types of decoders, let me just explain what is the logic behind decoding. Suppose we wish to know when a binary 1010 occurs at the inputs of a digital circuit. So, to indicate the presence of 1010 at the input, a high signal must be produced at the output. We know that an AND gate produces a high output only when all of its inputs are high. So, we can use an AND gate here to serve this purpose. We have to make sure that all the inputs to the AND gate are high when the binary number 1010 comes. How can we design this? Let A, B, C, D be the input bits. To obtain all ones or high signals at the AND gate, we need to connect A and C as it is and B and D in their inverted form, that is B complement and D complement. See the circuit given here? The bits B and D are complemented so that we obtain a high value output. This can also be implemented with a NAND gate if we require a low signal at the output. This is the actual decoding logic. Here we considered only a single 4-bit combination. In order to decode all n-bit combinations, we require 2 raised to n AND gates. Now we start with different types of decoders. Depends on the number of inputs, the decoders are classified into various types. Let us first discuss a 2 to 4 line decoder. 2 to 4 line decoder. Here the 2 inputs are decoded to 4 outputs, where each output corresponds to one of the minterm of 2 variables. Let A0, A1 be the input bits to this decoder. We can call them data inputs. The 4 outputs are Y0, Y1, Y2 and Y3. For each combination of inputs, one of these 4 outputs will be 1. When A0 A1 is 0 0, Y0 will be high. When A0 A1 is 0 1, Y1 will be active high. Similarly, the other two combinations are also detected. Look at the block diagram. We have 2 inputs and 4 outputs. A decoder usually has one more additional input line called as enable. This is used to enable or disable the decoder. The output will be generated only when the enable signal is high. This signal can also be shown in the logic diagram. Next, we are going to see how to write the truth table for this 2 to 4 line decoder. Let us write all inputs A1, A0 and the enable signal E. The 2-bit binary combinations are 00, 01, 10 and 11. Now, what are the output values? When E equal to 0, the decoder doesn't function. So, we write the inputs as don't cares and it doesn't output anything. Enter 0 for that case. Then, when E equal to 1, the decoder is in enable mode. So, it has to produce the output. When the binary 00 appears at the input, the output will be Y0. So, for input 00, we write Y0 output as 1. All remaining outputs are 0. Similarly, when the binary 01 appears at the input, the output will be Y1. So, for input 01, we write Y1 output as 1. Other output values are 0. And the same is done for the other two cases. This is how we get the truth table for a decoder circuit as given here. The logical expression for the terms Y0, Y1, Y2 and Y3 can be derived from this truth table. You may recall from the previous sessions how to write logical expressions from truth table. Y3 is 1 when all the inputs are 1. So, we write Y3 equal to E dot A1 dot A0. Similarly, Y2 can be written as E dot A1 dot A0 complement because Y2 is 1 when E is 1, A1 is 1 and A0 is 0. Then Y1 equal to E dot A1 complement dot A0, Y0 equal to E dot A1 complement dot A0 complement. The next, let us design the logic circuit. In the beginning of the session, we have discussed the decoding logic. To detect a specific binary input, we used an AND gate. So, here we have 4 input combinations and hence 4 AND gates. Each AND gate is fed with 2 data inputs A0, A1 either in complemented or uncomplemented form and the enable signal. The first AND gate is fed with A0, A1 and E. The inputs to the second AND gate are A0, A1 complement and E. For the third AND gate from the top, the inputs are A0 complement, A1 and E. Then the last AND gate is fed with A0 complement, A1 complement and E. When E is high, the binary value represented by A1 A0 will be reflected through one of the output line. Now, we have seen the logic diagram, truth table and logical circuit of a 2 to 4 line decoder. The next, let us design a 3 to 8 line decoder. 3 to 8 line decoder. This circuit, the 3 to 8 line decoder, is also known as binary to octal decoder. In a 3 to 8 line decoder, there are total of 3 inputs A0, A1, A2 and 8 outputs Y0, Y1, Y2, Y3, Y4, Y5, Y6 and Y7. Let us implement it using the enable signal. We draw the block diagram now. Draw 3 inputs A0, A1 and A2, then the enable signal and 8 output lines. This is the block diagram of a 3 to 8 line decoder. Then we write the truth table with all 3 inputs and 8 outputs. The output is generated only when E equal to 1. When E is 1, and inputs are 0, 0, 0, Y0 will be high. When the inputs are 0, 0, 1, Y1 will be high. In the same way, the presence of each specific combination is indicated by producing a high on its corresponding output line. When E equal to 0, the inputs are considered as don't cares and no output is generated. Now, we can derive the logical expressions for each output y0 to y7. y0 equal to 1 when all a0, a1 and a2 are 0. So, to obtain a 1 at the output, we use the expression y0 equal to E dot a2 complement dot a1 complement dot a0 complement. Similarly, we can write equation for all output lines as y1 equal to E dot a2 complement a1 complement a0. y2 equal to E dot a2 complement a1 a0 complement etc. And finally, we can write y7 equal to E dot a2 dot a1 dot a0. Next, we draw the logical circuit. Logical circuit can be designed as shown here. The three inputs A2, A1 and A0 are connected either in true form or in inverted form to the AND gates with the enable signal. The three inverters provides the complement. When 0 0 0 is given, y0 will be active high because the AND gate that produces y0 is connected to A2 complement, A1 complement and A0 complement using inverters. Similarly, we are able to decode all input combinations from 0 0 0 to 1 1 1. This decoder can be used to binary to octal conversion. The input variables represent the octal number and the output lines represent the 8 digits of octal number system. The next we are going to discuss on 4 to 16 line decoder. 4 to 16 line decoder. In a 4 to 16 line decoder, there are total of 16 outputs y0 to y15 and 4 inputs a0, a1, a2 and a3. The 4 to 16 line decoder can be implemented as we did for previous decoders, but more efficiently we can construct it using lower order decoders such as 2 to 4 line decoders or 3 to 8 line decoders. The number of lower order decoders to be used to implement a higher order decoder is obtained by a formula M2 by M1, where M1 is the number of outputs for the lower order decoder and M2 is the number of outputs for the higher order decoder. To illustrate, let us design a 4 to 16 decoder using 3 to 8 decoders. Then the number of outputs for the lower order decoder 3 to 8 decoder M1 equal to 8 and the number of outputs for the higher order decoder, that is 4 to 16 decoder M2 equal to 16. So, the required number of 3 to 8 decoders to implement a 4 to 16 decoder is M2 by M1 equal to 16 by 8, that is equal to 2. So, we are going to use 2 3 to 8 line decoders for constructing a 4 to 16 decoder. We have already learnt the working of 3 to 8 decoder, its truth table and the logic circuit. Now, we go for implementation. As I said above, 2 3 to 8 decoders are used with 3 inputs A0, A1 and A2. Out of the 4 inputs of the 4 to 16 decoder, A3, the MSB is going to act as the enable signal. See the logic diagram given here? A3 is connected to the upper decoder and A3 complement is connected to the lower decoder. So, when A3 is 0, the upper decoder is disabled and the lower decoder functions as a 3 to 8 decoder. So, the 4 input lines of 4 to 16 decoder are treated as 3 input lines and 1 enable signal. And the 16 outputs are y0 to y7 produced from the upper decoder and y8 to y15 produced from the lower decoder. You will be more clear about this design when you refer the truth table. The 4 inputs and 16 outputs are written here. The most significant bit A3 takes a value 0 for the first 8 input combinations and produce the outputs y0 to y7. It takes a value 1 for the next 8 combinations and produce the outputs Y8 to Y15. The binary values of A2, A1 and A0 are the same for both the cases. This is the reason of keeping A3 as the enable signal. The logical expression of the terms Y0, Y1, Y2 etc. Y15 can be derived from the truth table as Y0 equal to A0 complement A1 complement A2 complement A3 complement, Y1 equal to A0 complement A1 complement A2 complement A3 etc. Finally, we will get the term Y15 equal to A0 A1 A2 complement A3. Hope you have understood the above truth table and the expressions. Using this, we can draw the logic circuit as shown here with 16 AND gates and 4 input lines with complemented values. Next, we are going to discuss a special type of decoder, BCD to decimal decoder. BCD to decimal decoder. The BCD to decimal decoder converts each BCD code word into one of the 10 possible decimal digits. You may remember that a BCD code word has 4 bits and it can take values from 0 to 9. Here the input is a 4-bit binary number and its equivalent decimal digit is the output. As we know, it needs only 10 output lines that represent 0 to 9. So, this decoder is also referred as 4 to 10 decoder. The method of implementation is similar to the 4 to 16 line decoder. The logic used in the first 10 decoding gates of 4 to 16 decoder is only to be implemented here. The BCD inputs are given as A3, A2, A1, A0. We get the corresponding decimal at the output after decoding. Since it is BCD, only 0 through 9 can be given as inputs. See the logic diagram. The next is a BCD to 7 segment decoder. BCD to 7 segment decoder. While discussing about binary codes, we had gone through BCD numbers. In binary coded decimal encoding scheme, each of the decimal numbers 0 to 9 is represented by its equivalent binary pattern, which is generally of 4 bits. A digital system like a computer can understand and easily read a large number in binary format. However, a human cannot read large binary numbers. To solve this problem, we need to display it as a decimal digit using 7 segment display. Here let me introduce you a special decoder which can convert binary coded decimal into decimal, which can be easily displayed through a 7 segment display. We know that there are 10 digits in the decimal system, and to represent all 10 digits we need 10 combinations of 4 binary bits as shown in the truth table. This type of decoder accepts the BCD code on its input and provides output to the 7 segment display device to produce a decimal display. We already had a brief narration of 7 segment LED in one of the previous session. The 7 segment LED has 7 segments as the name indicates. They are A, B, C, D, E, F and G as shown in the figure. Each of these segments is an LED that emits light when current flows through it. Now, to display the digit 0, which are the legs to be energized or activated? All except G. And to display 1, only 2 segments B and C. Likewise, let us note down the segments to be energized to display all 9 digits. See the table here? Writing a truth table for this will help you to understand this better. The 4-bit BCD is given as the input. Outputs are the 7 segments that is to be energized for the display of each digit. The logical expression for each segment can be derived from this truth table. This can be expressed in sum of products expression. Look at the truth table. The output A is 1 for the inputs 0, 2, 3, 5, 6, 7, 8 and 9. So, we use those corresponding minterms to get the expression. So, the expression for segment A is A equal to F1 of ABCD equal to summation of 0, 2, 3, 5, 6, 7, 8, 9. In the same manner, we can write expressions for all segments. B F2 of ABCD equal to summation 0, 1, 2, 3, 4, 7, 8, 9. C F3 of ABCD which is equal to summation 0, 1, 3, 4, 5, 6, 7, 8, 9, and we get all the terms like this. Next, we are going to minimize these expressions to build a simplified logic circuit. For the same, it is much easier to use a K-map. Simplifying logic expression using K-map was discussed in the previous sessions. You can refer modules 14 and 15 to get a better understanding on this topic. To simplify the expression for A, F1 of ABCD equal to summation 0, 2, 3, 5, 6, 7, 8, 9, we map it onto a K-map as shown here. As we give inputs in BCD, the terms 10 to 15 are invalid and they are marked as don't cares in the K-map. While grouping ones, we get 2 quads and 2 octets. And the simplified function for A can be written as B complement D complement plus BD plus A plus C. In a similar way, we get equations for all the segments. You can try to get the minimized functions by yourself. They are A equal to A plus C plus BD plus B complement D complement, B equal to B complement plus C complement D complement plus CD, C equal to B plus C complement plus D, D equal to B complement D complement plus CD complement plus B C complement D plus B complement C plus A, E equal to B complement D complement plus C D complement, F equal to A plus C complement D complement plus B C complement plus B D complement, and G equal to A plus B C complement plus B complement C plus C D complement. Now, we are with logical functions for all 7 segments. Using this, we can draw the logic circuit as shown here. By now, we have completed the first part. When we input a BCD code, the corresponding output lines will be in active high. The output lines A to G of the 7 segment decoder are connected to the corresponding A to G of LED display. So, when you input a code 1001, the output will be in high at A, B, C, D, F and G. As these lines are connected to the same segments of LED display, those segments are activated and the number 9 is displayed. The 7 segment display are used in wide variety of applications such as digital clocks, electronic meters, etc. With little modification, this can also be used to display alphabets. Very commonly, it is used as a timer circuit. By this, I conclude the discussion on different types of decoders. Next, we will have a brief description on the applications of decoders. Where do we use decoders? Decoders are greatly used in applications where the particular output or group of outputs to be activated only on the occurrence of a specific combination of input levels. This can be used as a timer to turn on or turn off the devices at specific times. One of the important application is in memory systems of computers to minimize the effects of system coding. Decoder is also used for implementing combinational logic. Combinational logic implementation. We know that decoder produces 2 raised to n minterms of n input variables. Also, we have learnt that any Boolean function can be expressed in its sum of products form. Here, decoder generated the minterms and by using and OR gate we can find the sum of minterms. So, any combinational circuit with n inputs and m outputs can be realized using an n to 2 raised to n decoder and m OR gates. For example, let us implement a full adder circuit by a decoder. You may refer to module 16 to refresh on the topic full adders. There we have derived the expression for sum and carry of a full adder. The expression for sum is sum of ABC equal to summation 1247, and for carry, carry of ABC equal to summation 3567. Here we have 3 inputs and 8 minterms. So, we use a 3 to 8 line decoder as shown here. This decoder generates all minterms of a 3 variable Boolean function. Out of this, the minterms of sum function are logically ORed to obtain the sum output, and minterms of carry function are logically ORed to generate the carry output. If the number of minterms in a function f are more than half of 2 raised to n, it is advisable to use NOR gate to sum the minterms of f complement. The output of NOR gate will produce the actual output f. Likewise, any combinational logic can be implemented using a decoder. That is all about decoders. Let me summarize. A decoder is a digital circuit that detects the presence of a particular binary sequence at the input level and indicates the same at the output level. There are different types of decoders: 2 to 4, 3 to 8 and 4 to 16 line decoders, or in general we say n to m decoders, where n is the number of input bits and m is 2 raised to n, the number of unique outputs. When some of the output lines are invalid, the number of output lines will be less than 2 raised to n. One of the example for this is BCD to decimal decoder. Another special circuit, the BCD to 7 segment decoder, was also described in detail. At last, we discussed about combinational logic implementation using decoder. With this, let me conclude. We will continue with more combinational circuits in the next session. Thank you for watching. Bye.